chemistry, this is something that perhaps many of you were not so familiar with when you were students, but that's a relatively new change here in the department. I believe that before the year 2000, we might have had one faculty doing simulations, and that might have been Byers, perhaps. I think Desi also worked a little bit on simulations. Well, that has changed now dramatically. We have 4 faculty members who are theorists. We don't have a wet lab. Okay, so the last experiment that I did in the lab was when I was an undergrad, right? And that was maybe 18 years ago, right? So we have offices and we have labs, but our labs are just full of computers. That's essentially what we do. Yet this is an very important part of chemistry, as I will show you just a little bit. All right, so notice that we're 28, I think, full-fledged faculty members, and 4 of us are theories. So now theory is about 15% of the entire research enterprise of this department. Okay, and I think it's only going to grow larger in the future. All right, so chronologically, Daniel was the first. He came, I think, in the year 2000, 1999. I came in 2004. Then Ed came 2 years after me, 2006. And Nick is our latest incorporation. He came about 3-4 years ago, I believe, 4 years maybe. All of us, I think, have been very successful, right? So we're 444 in NSF Career Awards, which are kind of the hallmark early career awards that you can get. There's 2 direct medalists. This direct medal is awarded to the best quantum chemist in the world under the age of 40. Right, so both Ed and sorry, Daniel and Ed have gotten. I'm pretty sure Nick will. I don't know whether they pass my clients, so I will be. But we're very active, right? So there's about 10 plus active grants among the 4 of us. And again, this is a private enterprise. All right, so what do we do? As you will see from my slides, we really like to guide experiments, right? So we kind of have the tools to be able to interface quite well with a variety of experiments. But we also develop theory. You guys remember your quantum chemistry, right? And that equation is only solvable exactly when you have 1 electron, right? Once you have 2 or more, then you can solve it exactly. You have to solve it approximately, right? So this will never end. There's always better approximations that you can use to solve that equation, right? In particular, we're interested in trying to apply this as accurately as possible to larger and larger systems so that eventually we can model things like DNA, polymers, and so forth. We're not there yet, but that's great news because that means that there's a lot of work that we can do. Now, the idea is that the solution of this equation is tied to the computational hardware that you can use, and that is also changing dramatically. Right? So quite a bit of the effort is now trying to see how we can port the solution of this equation to state-of-the-art architectures including quantum computers. And I'll tell you more about that just a little bit. All right, so a little bit of this interface with experiments. Already my colleague John Morris has told you about this chemical warfare agent project. And this is actually pretty recent. We never heard about that in the news, but this is still being used today, right? So this is a piece of news from 2 years ago where in Syria it was detected that people still are using sarin and mustard gas and these agents, right? I mean, we have stockpiles of them, and those are worrisome, but they are easy to synthesize, right? So people can use them indiscriminately, and so that's a worry, right? A concern. Right. So what we've been looking at in this project is a variety of materials which are fairly exotic. When I actually started in computational chemistry, I was worried about this bit of the periodic table, maybe that line, the hydrogen for sure, but then those elements, that's it, right? And now when you look at these materials, now I'm going deep in the periodic table. That's an niobium atom, that's a cesium atom, that's really down here, right? Niobium, cesium, zirconium. But these have excellent chemical properties for chemical warfare agents, and we're trying to see which one of these is going to be the one that acts as a catalyst, right? So ideally, what we'd like to have is perhaps a topical cream that you can actually use as a sunscreen, and then if a chemical warfare agent is released and it gets to your skin, right? That cream is going to be able to hydrolyze that nerve agent, and you can survive, right? So that would be the ideal situation. We're not there yet for sure. Anyways, this is a large collaboration, and you know that you've made it when you actually are in a team that has its own Google Scholar site, right? So generally the way that we keep our citations recently is with Google Scholar. Now you can do that for your team, right? So this is the publications that, I guess that the computer did not want to cooperate here. Let's see if I can show you that. Let's see. Anyways, we do have about 16 publications in the last 3 years or so, so this has been a pretty productive aspect. So let me show you here the results that I have right here. So this is what happens in the experiment. So you mix these nerve agents or stimulants with the surfaces, and then you measure spectra, and now the goal is to try to unravel what the changes are, to see the reaction, what type of reaction. This can be exceedingly complicated, right? What we actually can do in the simulations is exactly the same thing. We mix the reagents, but now we have an atomic control on what's going on, right? So this is serine, right? There's phosphorus and then fluorine. That's the bond that you want to hydrolyze, and this is your hexaniobate. And you have water here, right? So this is going to be a hydrolysis reaction in which that material, that hexaniobate, is going to be able to hydrolyze the nerve agents, right? So this water molecule is going to dissociate on that oxygen atom, and then the nascent hydroxide adds to the nerve agent, and it turns out that this is then very labile and it falls apart very easily. Right, so there's how the complement you can feel in an experiment, right? In the experiment, you always going to have this level of atomic understanding, right? But it's never there. You always have to interpret your spectra. Now, with simulations, this is approximate, right? So these are models, okay? But the models are faithful enough that if you're able to match the spectrum, then you can believe the story that you're being told there. And we actually can match those spectra, right? So you can actually calculate the spectra, and we can identify variations that are actually quite important, right? So here's what happens to that niobate, right? And this is the Raman spectrum, and we can actually capture that there's a shift from the unreacted niobate to the reacted niobate, which tracks quite well with the experiment, and then that kind of lends confidence to the theory that we're using in the models. So a couple slides about my colleagues. So Crawford, he really likes to study chiral properties of molecules, right? So ideally what he wants to do is just have a molecule with maybe 10 stereocenters and be able to calculate the optical rotation for that molecule. That would be extremely useful in the assignment of the absolute configuration of drugs and things like that. Ed is trying to solve the general equation as accurately as he can for very large molecules. And then Nick is working on algorithms for quantum computing. Right, so this is a little bit of where the field is going. Right, so right now what we're actually trying to do is write codes that can be used in exascale computers. Okay, so what is an exascale computer? An exaflop is all of these operations per second. Okay, so that means that every human on Earth would need to be doing one operation per second for 4.5 years. Okay, so every human doing, say, an addition every second for 4.5 years, these computers can do it in 1 second. Right, so the idea is how do you actually write code so that you can leverage that incredible computing power, okay? And this is part of federal an investment, heavy investment, $2 billion in building these computers and disseminating them through national labs and things like that. This is what Mejo is working on, right? The idea is that if they ever work, they're going to provide a tremendous platform to solve these complicated equations. That part of the operations are done in regular computers, and part of the operations are done in the quantum computers, because those operations are very well suited to the quantum computers, right? So that's kind of where this is going. Ultimately, we're just trying to develop tools for doing chemistry, but this is essentially what we're doing. Right, great. So we are leading the country and the world, actually, with many of our efforts, right? So this is the famous Molecular Sciences Software Institute by Crawford. Okay, so this is $19.5 million from the National Science Foundation, which is expected to be renewed for up to 10 years. And this is part of a White House National Strategic Computer Initiative, right? So this was a big boon for us. This has really put us in the map, and we can see that because every time that we have a faculty position, people actually, many of the theories in the country want to come work here, and this has been a great change since my time. All right, so I noticed that there is a multi-university collaboration with people from UC Berkeley, Stanford, and a variety of universities. Anyway, so hopefully I've been able to showcase a little bit the theory efforts here in the department, and I'll be happy to take some questions.